Right, do you want to go through that last thing we did last time? So we're saying like 30 works, right? 30 was what was it? 3, 4, 5, Addy? Is that right? Yeah. Saying 30 works, and then we want to show that all the 30 plus 60 works for all the multiples of 60. Yeah. Like 30 plus 60 and also 3, 4, 5 adding, right? Yeah, so what I want to say by induction is like you can say that you can prove for the first one, so that's the lowest one when n is 0, right? This is n equals 0, you know? And then you can assume that like you want to show that anytime one value is true, the next one's true. So then if you can prove those two things, then you can conclude that any value of n will be true, because you can always get from any value from 0 to any value of n. Yeah. So if n equals k, right? We're saying that this number here, let's say like this 30 plus 60k, right, is equal to like, you know, x minus 1 plus x plus 1, right? It's also equal to, you know, y minus 1 plus y plus 1 plus y plus 2, right? And it's also equal to z minus 2 plus z minus 1 plus z plus 1 plus z plus 2, right? I mean, this we can do it directly, but I just want to illustrate what induction is. Okay, so if that's the case, then we assume this is true, yeah? And then we want to prove that that implies the next one's true, okay? So it's plus 60k plus 1, yeah? So what this is, it's equal to 30 plus 60k. So that's the old one, right? Plus another 60, yeah? So it's equal to all of these things plus 60, yeah? So it's equal to x minus 1 plus x plus 1, y minus 1 plus y plus y plus 1 plus y plus 2, right? Z minus 2 plus z minus 1 plus z plus 1 plus z plus 2, right? I guess the key here is now you're adding 60 to all this, right? Plus 60 to each one of them, right? The key is that 60 is divisible by 3, 4, and 5. So you can actually split it up as plus 20, 20, 20, right? So then it's the sum of consecutive numbers. So this is x minus 19, x plus 19, x plus 20, x plus 21, right? And then this one is plus 15, yeah? There's y plus 14, y plus 15, y plus 16, y plus 17, yeah? And then this one, you see it's a fifth of 60 is 12, yeah? So this will be z plus 10, z plus 11, z plus 12, z plus 13, z plus 20. So if the previous one was all these things, then the next one is as well, yeah? Because these are all consecutive, yeah? So therefore, you know, like, and so that's meant to be finished. That's you're done. And the reason you're done is because, well, it works for 30, right? So that's as if that's like the previous one here. That's like k equals 0, right? And you showed that anytime it worked for k, it worked for k plus 1. So then therefore it works for 30 plus 60. Okay, and since it works for 30 plus 60, it works for n equals 1, right? And you showed that anytime it works for n equals 1, it works for n equals 2. So no matter what n is, you can always get from 0 to n infinitely many steps like this, right? Like 0 to 1, 1 to 2, 2 to 3, all the way up to whatever n would be, yeah? So that's what induction is. Yeah, I guess this one you didn't have to, because I think you showed some result where it's like it's 3 addy if and only if it's divisible by 3, yeah? but you just didn't say only if. Yeah. So then you could say, well, then it's 3, 4, and then you proved that 5 addy if and only if it was divisible by 5, right? But you didn't say that only if. But it's kind of obvious, but you got to. I think it's important to be aware of it. And so it's 4 addy if and only if it's not divisible by 4 but divisible by 2. Okay, and then therefore it's these simultaneously if and only if those 3 conditions simultaneously. And so therefore 30 plus 60n is divisible by 3, 5, not 4, and divisible by 2. And so then all those numbers are satisfy this question. Yeah. Did you guys prove why the 3, 4, 5? So we had to prove why 2 and 4 addy was impossible, right? From last lesson, I think. So it was like you said this meant it was odd, right? And then this meant it was even.
Yeah.
So it can't be odd and even. But why was 3, 4, 5, 6 addy impossible? I guess this is where the working saved time for the second part, depending on what you did for the first part.
4 means 4 addy means even. 6 addy means 6x plus 15. So it will be both odd and even.
Both odd and even.
Yeah, because 6 plus if it's 6 addy, then you'll be in the form of 6 y plus 15.
Is it like what y?
Oh, so it's 2. Oh yeah, because you're saying So I'm thinking of your thing because 6 addy means it's divisible by 3 but not divisible by 6. So that means it's odd, yeah. And then 4 addy means it's even, yeah. So it's the same kind of idea. Yeah. Okay, good.
What was this? What did he do?
Oh, so he proved in general that any odd number, so if it's like 3 addy, right? Because 3 is odd, it means that so it's 3 addy if and only if the number is divisible by 3. It's because if it's 3 addy, right, then it's z minus 1, z, and z plus 1, right? So that's 3z, so it's divisible by 3. Okay. Conversely, if it's divisible by 3, right, you can write it as 3z, and you can write 3z as z plus z minus 1 plus z plus 1, yeah? Yeah, well, 3z. Wait, hold on. If you can write it as 3z, do they have to be positive integers?
Yeah. Oh, right. Okay, sure.
Yeah. 3z minus 1. Yeah, I guess the problem is 3 is not 3 addy, yeah? So it's 3 addy. So if it's 3, it's if and only if it's a multiple of 3 but not 3, I guess, yeah? So is that a problem? So yeah, 3 is not 3 addy. Unless you have negative numbers. Okay.
You can't use 0.
Huh?
You can't use 0.
Yeah. So even with 0.
Get 0.
Yeah. Oh, yeah, okay. Can we use 0?
I'm not sure. Because I don't think it said positive integers. So that must be kind of bad.
Okay, but you get the point, right? There may be some minor things you have to consider to be logically accurate. Okay, good. So that finished off that one. What other ones are readily available to talk about? Do you want a more interactive one? But then again, the more interactive ones are the ones that I know you haven't had time to really try. So they're definitely going to be more interactive. The less interactive ones are the ones I reckon you've already done. So so that was number one. I'm pretty sure you did that. Did you all end up doing question 3?
No.
Or did you want to do question 1? Because you've done question 1. Did you all get question 1?
Mm-hmm.
Anyone want to show us? You want to tell me what to do? So for each pair of real numbers, so this is 2017. Question 1, yeah? You got a pair of real numbers, R and S. For each pair, prove that there exists a real number X. This is, I guess, one way to say a pair of real numbers that satisfies at least one of the following equations. At least one. Just like, whatever. There's no like equation loyalty, I guess. How do we do it? Discriminant. Oh, so you're just saying at least one of these has solutions. Okay, so the discriminant, the real X. Okay, so the discriminant. So the discriminant of 1, right, is equal to 4s. Okay. Do we need to do any more of that? And this is 4s squared minus 4rs. Oh, okay. Stuff to do, yeah. 4s. Okay, so yeah, so we don't really need a 4 because we only care about whether this is positive. Yeah. It's okay to be. It's allowed to be 0. Yeah.
Yeah.
All right. So it's greater than or equal to 0 if both these are positive or both are negative. Yeah. What do we do next? So this is either S is greater than or equal to 0 and S is greater than or equal to R, right? Or S is less than or equal to 0. S is less than or equal to R. Less than strictly. No, it doesn't matter. It's the same. Yeah.
We can do contradiction.
Okay.
Don't just list all the possibilities. Like you let S, you let S always be with R. R always be with S.
Oh, okay, so you go from here.
Yeah.
So it could be either this or this, right?
Yeah.
So it could be either A or B. Yeah.
Mm-hmm.
And if it's A, what happens? S is bigger than 0.
Use 2 to show that it's bigger than R.
Okay, so if S is so where we start? Are we dealing with this equation at all?
Mm-hmm.
I did. If S is larger or equal to R, then you can see that S is larger than R. larger or equal to Rs, and then
Oh, so you're saying if S is greater than or equal to R, right? Then S squared
it's
or
not
R
just
squared?
S and
S squared is greater than or equal to.
Rs.
Alright, okay.
And move the Rs to one side, and you see that S squared minus R is larger or equal to 0.
Okay, so you need S to be positive, yeah? Is it?
No, I don't think so.
Yes, sir.
I think it's
So,
What's the logic then?
no, it doesn't. You don't need to. Wait,
so S is bigger than equal to R.
Well, like, what if S was like -1, R was -2?
yeah,
No,
yeah,
Oh.
yeah.
Yeah, then 1 is not bigger than or equal to 4 or 2, right?
I use this way, so I put like this two equation, either R is bigger or equal to S, or S is bigger or equal to R. And then those two I can divide up to further.
Oh, so you're starting with an arbitrary RS.
Mhm.
Okay, that's good. Okay.
And then
Okay, so let's see how this proof will go then. Okay. So we want to show for all RS. So let RS in R2. Yeah. So that's a set of ordered pairs of real numbers.
Yeah.
Okay. And then you said either R is bigger than or equal to S,
Mhm.
or R is less than S, right?
less or equal to S.
Oh,
S is
yeah,
bigger or equal to R.
Okay, I guess you want some overlap.
Yeah, thank you. And then you can I think
So if R is bigger than or equal to S, or which one do you want to do first?
okay, R is bigger or equal to S.
Yeah.
Then you can use the first equation
The first equation.
Mhm.
Yes.
to prove that for all R negative or positive, R plus 1 squared minus 4 is always, so it's in a positive or 0.
So this will always be positive. So you're saying this?
Mhm.
If that, then this?
Yeah.
Oh. Let me show that. Let's see.
alright, so the minimum value of that of like the first one would be if S was equal to R.
Uh-huh.
So then it's something like if S is equal to R,
Yeah.
then if you like expand the R plus 1 squared, you end up with R minus 1 squared,
Minus 1 squared.
which is positive. And since that's the maximum value of S, that means all other like values of S will be smaller than that.
Oh, you're doing this thing.
Yep.
Oh, so you're saying this is minusing something.
Yeah.
So if you want it to be maximum, you want to minus the biggest thing possible.
If on minimum, yeah.
Yeah. So then you minus. So you turn this into 4. Yes. This is R plus 1 squared minus 4R, right? It's greater than that. Yeah. And this is equal to R minus 1 squared. Yeah. Which is greater than or equal to 0. Okay. Great. Excellent. Oh, some elegance about it. Yes. And then what if R is less than S?
You can use the second equation.
Use the second equation. Okay, so R is less than or equal to S.
I did S is greater or equal to R, so that way.
Alright, S is greater than or equal to R. Okay.
And then you can you can solve it for S. It doesn't really matter. And since S is always going to be greater than R, and S minus R, like for S is greater than 0, for S times S minus R always is greater than 0. And for S
Wait, so you're saying this will always be greater than 0?
yeah, for S
Just from this or
If
something?
S is greater than 0.
0.
Oh, okay. So if S is greater than or equal to 0, then we're in case A, yeah?
Yeah.
Then we're going to A, yeah?
Mhm.
But if we have, but if there, then and S is less than 0?
Yeah.
It's negative.
Yeah, then you flip around this side, and then you can prove that. And 4 is minus 4 will always be smaller than 0. So
You flip what sign?
So 4S is smaller than 0.
Yeah.
Because of 4S, the sign will be flipped.
This
So
one.
I know the bottom one, second equation. So 4S times S minus R.
Oh, I don't think we can get anything from the second equation.
I think you can because
we have explicit conditions.
like well, if s is less than 0,
If s is less than 0, then
then
4s
4s is negative.
And so it's
Yeah.
minus r.
And if r is less than s, then s minus r is going to be greater than 0.
It's also negative. So
Smaller than 0.
It's smaller than 0. Yeah.
No, we have for the second equation, right? There has to be these two conditions.
Alright.
So if once you have s is greater than or equal to r, right? And so therefore it can't be b, yeah? And s is not bigger than or equal to 0, then this equation cannot help you.
No, but then it says it doesn't matter which one it satisfies. So
Right,
you
no.
can either intact.
But
Yeah,
look- But look, it actually satisfies that one, right?
Yeah, 'cause
because when it's
if
negative,
s is less than 0, then 4s is minus
Positive.
4s is positive,
yeah.
and upper squared is greater than or equal to 0.
See what I mean? So like the reason that it can't be this one because these are these conditions are like characterizing, you know. They're positive. This is positive if and only if A or B. Yeah, so it's either this, in which case it's A, or it's this, in which case it's not B or A, so it has to be this one, right? So if it's this, then minus 4s is greater than 0, yeah? And if minus 4s is greater than 0, and that's positive, then the whole thing is positive. Square is positive. So positive plus positive, yeah? Yeah, no, that was good though. It was just one minor thing at the end. Yeah. Yeah, I discovered it's a red pen when I write. And it pretends that it should be, I guess, yeah. Alright, we good with that one? Yeah. So yeah, like this one actually, that's the good thing about algebra is you can be really rigorous with algebra, right? It's like let this be arbitrary, then it has to be these two. If it's this, then that. If it's this, then that. And if it's that, then this. If it's that, then that. You know what I mean? It's like completely, it's like closed. Okay, how do we solve? Okay, remember just, huh?
Did you want to do it?
I haven't looked at it. You want to do it?
Yeah, sure.
No? There's no one. I'll do the powers of 2 next after this one.
So basically, you have a quadrilateral. The width side, like the sides A, B, and you have a circle that's with this is the diameter, and this is tangent to another. This is tangent to the other side of the quadrilateral. So, and the diameter of and the circle is such that this line is diameter is also yes.
So we don't have any. So we have 2 circles and 2 diameters.
Yep.
You know.
And they intersect at the circle at AB with diameter AB is tangent to CD at X, and then the circle at CD is tangent to AB at Y.
Mm.
And it asks you to prove that
Cyclic what?
BDXY is cyclic. Yes.
Does that make AYX be cyclic too? Oh.
It should. So BCXY. The way I did this was if you just draw in these lines.
Wait, where did you what?
Is there another color?
Yeah. That's also blue. No. That one's red.
So if you draw these lines and these lines here,
90s.
so this is diameter, right? So this is 90 degrees.
Mhm.
And then, so if we let this angle will be alpha. So AB is tangent to the circle, right? So that means that this angle here is equal to this angle here because alternate segment theorem.
What?
Basically,
Oh, yeah.
Yep. So then so now we do something here. So this angle is beta, we call this angle beta. And then, so same thing as we did before.
It's good when people know some of these facts.
These
Because
are,
it's much more tiring when you have to prove every one of those as you go.
yeah, so this is 90, so this is 90 minus beta.
We're all good so far.
And this is, so same thing here, this is beta. Right? And this angle here equals this angle here because vertically opposite. So that means these two must add up to equal these two. Because some will
Which
try.
two?
So this angle and this angle
90 minus alpha plus beta.
plus 90 minus, yep. 90 minus alpha plus beta must equal to 90 minus beta plus alpha because these are equal and they add up to 180 each.
Oh yeah, they're not equal as it stands. So it's good that they're equal.
Yeah.
So that's telling
So
you
then-
something about.
You do this, you move them across, so 2 beta is equal to 2 alpha. So alpha equals beta. So then, and then since alpha equals beta, then that means this equals this. So since it's, so if these two angles are standing on this line, arc, then it's a cyclic chord.
Makes sense.
What is alpha? Which arc is that?
So they're both standing on y-axis, right?
Wait, what's the question?
Prove that BCXY cycle.
Oh no, what's Sean's question?
Oh, like which arc are they standing on? Okay, like how from this, how do we know?
Was
it's
that the
cycle?
question, or were you saying why are the alphas equal?
Which arc are the? Oh, because it's alternate segment, which I can't see.
Oh, he's trying to say how the alternate segment works.
Oh, okay.
Yeah, that's what I thought. So so this is the tangent, right? There's an angle between the tangent and the chord. Yeah. So the chord is dy.
So this is alpha, right? Then this chord, this part here, is is going to be this is alpha. Whatever. What do I explain? What's the best? Let's do it.
Wait, are you trying to prove the alternate segment?
Yeah. Just
You don't need proof.
Yeah,
I think you know it. You know
yeah.
it.
Good. So this is alpha. This is alpha. This is beta. This is beta.
Yeah. So the tangent is the angle with the chord yd,
This one
and then yd makes an angle. Let's see.
makes this angle. So this angle here is between. This angle is AYD, right?
Yeah.
So the chord and the tangent is AB, and the chord is YD. So it's like
Yeah. You can draw a diagram that just has that. Yeah. That's good.
Y. So that's D and that's C here. That's B. Yep. And then same on the side. So then yeah. Inside.
So that was question 2, right?
Yep.
No, question 3. So what was it? It was like you have A1 less than A2 less than A3. So you have like they're all positive, are they? So you get over than 0. 2017. You got this one too, right?
Yeah.
And you have the same for B. This 2017 B's as well, right?
Mm-hmm.
And the properties that it satisfies is that 2 to the A1 plus 1, 2 to the A2 plus 1, all the way up to 2 to the A 2017. Like if you make them all the powers, they equal to the same thing with the B's, yeah? 2 to the B1 plus 1, and so on, yeah? And then if that's true, then A1 equals B1, so on, right? And they're all equal. Yeah. You guys, yeah. So this is, you can probably write this nice, like you can write this quicker if you have this in product notation. Have you seen that? So another way of saying it's like 2 to the alpha AI plus 1 product. It's like sigma notation. Have you seen sigma notation? But now it's a product. Yeah.
Oh, I just realized formalize my solution for the geometry for my x and y is the other way around.
Oh. Okay. Did you get any progress on this one? Haven't tried it?
Uh-huh.
Oh. Maybe we can do it like 2 minutes at a time. You have a try and see what like a first step might be. Huh? So we're trying to show that anytime if you have 2017 different powers of 2 plus 1 times together and they're equal, then the powers have to be the same. Does that make sense? I guess it shouldn't actually. Oh yeah. Okay. So yeah. Notice how like they're ordered, so you don't have to reorder them when you match them up, right? It's not like there'll be like a 4 and an 8, and then a 3 or something, and you have to unjumble them. They're already ordered, so they have to actually already be equal to each other. Did you get the floors one? How far did you didn't give me anything?
I don't think like because I ended up using that one for a bit more. I don't think I had anything to conclude on this.
Oh, we can go through that one more interactively too. Do you have a nice one for this?
Might be nice.
We'll go through. So okay. Did we think to? So I guess it's unlikely that 2017 is going to be a special number here. Yeah, it's kind of just arbitrary lot. So actually, so we should probably try to generalize and specialize this, right? So just sort of any number of numbers, yeah, or one number, yeah. So I think a good thing to have a look at just to get a feel for the problem is just the easiest case, right?
Yeah.
There's just one factor. Or actually, maybe if so you can even think of if you don't care if they're positive, they probably, I don't know, does it work if they're negative? Anyway, so this is 2 to the A equals 2 to the B, right? So actually it works even if they're negative. Which means I guess you could take 0 to be A0, maybe. But anyway, so that works, yeah? And so this sort of induction idea, can't fit it in there. 2C plus 1. No, Did you try this one? Not saying it's the right thing to do, but what was it? 2D plus A plus 2A plus 2D plus 1 equals so the ones cancel again. I guess depending on whether A or B is or A or D is smaller, there's going to be a common factor, right? So if A is the smallest, yeah, let's just say A is the smallest and B is the smallest. Otherwise, well, actually no, we know that D and B are the smallest, yeah, because you write them in that order.
Yeah.
Okay, so should have made it A1 and A2 then. Okay, so D is the smallest, so this has got a common factor of 2 to the D, right?
Yeah.
And then it's odd now. Well, actually, maybe the A is the same. No, it's not the same, right?
No.
Okay, so the same thing happens here.
And those two work. And since the both sides have to have the same amount of powers too.
Yeah, so like 2 to the D has to divide 2 to the B. Because this is odd. And
2 to B has to divide 2
to the D, so D has to equal B, right? So if D equals B, then they cancel and you're back into this situation, right? The first situation. So that's kind of like an induction, you know? So basically, what happens if you have 3 of them? So you understand how that works? So then they have to be equal, yeah? What happens if you have 3 of them? So A1 plus 1. Okay, it's getting a bit harder, yeah? Two to the mean 2. Yeah, so this is like
expanded again.
2 to the a1 outside of 2 to the a2 plus 1, 2 to the a3 plus 1, right? Plus plus that, right? Plus this again. And then that's yeah. Yeah. So can you see basically once the ones cancel, right? So we have a 1 on both sides. Once the ones cancel, 2 to the a1 will divide everything else.
Like 2 to a1 is the highest power of 2 on this side.
Yeah. Yeah. Well, yeah. And so you can cancel it out. So a1 has to be equal to b1 because they're the same.
Yeah.
And then it's induction again. Okay.
So yeah, so then it's induction. But the question is how to write that in a nice way, you know? And also how to even write it at all. Is that even an argument you can actually do? Because how do you know it's an odd times?
Even plus 1.
Yeah, like so, you know, remember how we had induction? Induction was like we just basically have a general case. So we assume that you can anytime you have like n things equal to m things and they're equal, right? And then we prove that if it's n plus 1, you can reduce it to the n. So let's assume they're equal for n, right? Okay, whatever letter you want to use. Yeah. See if you can get rid of one of the the lowest, the a1 and the b1, right? Because we showed it works for n equals. We showed it's true for the first 2 cases. Okay, so how do we do it? Ones. So the one. Let's cancel the ones. Yeah. So -1 from both sides. Outside of. So this is outside of the product. 2 to the a. Plus 1. This is I equals 2. So m plus. Okay, plus 1. Yeah. And then plus.
Wait, right now isn't it just a k?
Huh?
Isn't it just a k? Or are you,
Oh, okay, sorry. Okay, plus 1. Yeah. So it's 2i times that. Okay. Plus 2 to the ai times. Maybe it's not so easy to write that out.
I think I have a like.
Yeah, I mean, so I was trying to avoid saying modular arithmetic.
Oh.
But do you know modular arithmetic?
I'm not very good at it. I know it's a little.
Yeah, so basically all it says is like if you have like a times b, like arithmetic is like multiplication and addition, right? Yeah. And if you take remainders, like if you have another letter like r, right? If you take the remainder, sorry, let's use the letter p, okay? If you take the remainder when you divide by p at the end of the calculation, it's the same as taking them before the calculation. You know that, right?
Yeah.
Oh, okay. Well, that saves some time. because then what you can do, well, we're just kind of going. So once you cancel out the 1, well, actually, you can even just look at mod. So, like for example, A1 could be. Let's assume that A1 is smaller than B1, right? Yeah. So then take mod 2 to the A1
plus 1.
or B1. Yeah.
No, that implies that what if like A2 is still smaller than B1?
Oh yeah.
So
So
you go ahead and A1 plus 1. Because then everything else is guaranteed to be like greater than or equal to
so if it's A1 plus 1, yeah. So this could be the same as B1. Yeah, but maybe not. But this is so A1 plus 1, I guess, is smaller than or equal to all the other AIs, yeah, and it's smaller than or equal to all the BIs, yeah. Does that make sense? But it's obviously bigger than A1, yeah. So if you take it mod A1 plus 1, then this is going to be 0, right?
Yeah.
Right. So all of them. So all the other ones on the other side, right?
Yeah.
So what you get is you get mod 2a plus 1. It's you get 2a1 plus 1 times 1 times 1, right? Equals 1 times 1 times 1.
Yeah.
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 So the problem with that is, so this is just equal. So this is saying 2a1 plus 1 equals 1 mod 2a1 plus 1. Yeah. So, or in other words, this is equal to 0. Yeah. But it's not true because it's a smaller power of 2. It's not divisible by a bigger power of 2. Right?
Yeah.
So therefore, you know,
Yes.
they have to be equal because you could just do the same thing.
Oh, yeah.
Instead of saying A1, I just said that it's like the smallest, like, so assume it's in the a group with almost a generality, and such that it's the smallest one that's not in both.
Yeah, like what's the smallest one that's not
So
involved?
like say AN is the smallest power, like smallest term that's not in both that's not on both sides. So it's in the only appears once.
Oh, okay. So it's
Okay,
like
so
it's like the maximal version of induction.
Well, yeah.
Yeah.
And then everything else underneath it gets cancelled out, and then you end up with that.
Can you prove this by induction?
Yeah, I guess we just did, but we still had to use this idea. So what we did was we assumed. Okay, so what are we proving? Okay, so we're proving that we're actually proving if it's n, right, then b I equals ai rho I, yeah, and we're proving this by induction, yeah, induction on n, yeah. So if n equals 1, right, then we just kind of, it was kind of obvious, right? It's a1 plus 1 to b1 plus 1, and we showed that a1 equals b1. Yeah.
Yeah.
Yeah. So and then we assume, now we want to show that n equals k implies n equals k plus 1. The truth of n equals k implies the truth of n equals k. So we have that anytime you have k different numbers like this, so k And maybe you can call it like A. Yeah, okay. A I equals that. Right. I equals 1. Then AIs are equal to BIs. Yeah? That's the induction hypothesis. And then the induction step is, well, now you have some, but this is for any powers, right? That satisfy these conditions. You have k plus 1 I equals that. You have 2 AI right?
We take out the.
Then we use that trick to cancel out one of the. We use the trick to show that the lowest ones are equal. Yeah. So we show that A1 is equal to B1. Yeah.
Mhm.
And then because A1 is equal to B1, we cancel out that factor. Yeah. And then what you're left with is a product of k things, right? Equal to a product of k things where they satisfy those conditions.
And since we know that's correct, then they'll all be equal.
Yeah.
They're all equal.
Then they're all equal by the induction hypothesis. So like if it was 2, it was equal because 1 was true. Yeah. If it was 5, it'd be true because 4 was true. Yeah. Any questions about this? All good? Okay. All right, well, let's do this other floor question then. Yeah? Interactive. It's like some kind of single player game. What was the question? Remember? It was like, which primes? I still don't really understand how prime really comes into this nicely. Which primes P so the question is, which primes P have the property, huh?
One of the
That there exists an integer A, yeah?
Yeah.
Such that A over P floor, yeah, plus like all the multiples up to P, yeah? 3A over P. Is this right? And then 4 all the way up to what? It depends what P is, but like
P
all the way
A
up
F P
yeah?
equals 100.
I think it's 100, yeah? Or you can know sigma notation, I guess this is Ka over P. Where K is equal to 0 P, yeah? Is it K equals 1?
Yeah.
Sorry.
Or doesn't matter. But yeah.
Interactive problem number 1. We have like 2 minutes.
This question.
So did you guys try p equals 2?
Yeah.
Does it work?
No.
Huh?
No.
No.
Yes. Yeah. 67.
So what happens if p equals 2? So it's we need 100 equals a over 2 plus a, right? Is that right?
Yep.
And then, so basically you need a to be like around,
2/3 of 100.
yeah.
It doesn't aim to be integer.
So yeah, so let's say a equals 67. Wait, do you know what this symbol means?
Mm.
Oh, sorry, yeah, so this means like you always round it down to the integer. Like it's not even rounded down, you always cut off the not integer part. So like 3.33 becomes 3, 3.98 becomes 3. As long as it's not over, like it's like if the number is like 4 point something something, it goes to 4 if it's positive.
Oh, okay. Oops.
Oh, did you think these were absolute value symbols?
I still know the message statement.
Oh.
That could make it hard.
Wait, what did you say?
Yeah.
They sound like brackets at
He wasn't
first.
sure what they were, so
Yeah.
he just ignored them.
So it's like that.
Oh.
It's pretty fun. Yeah, so this is like yeah, the integer part of x. Well, not quite, but it's like if it's positive, then it's the integer part of x. Yeah, so it's the biggest integer less than or equal to x. Yeah. Okay. Yeah, so if a is 67, right? Then 67 on 2 is like 33 and a half, yeah? So 33 and a half, so 33 and a half, that gives you 33, yeah? And a is 67. So when you add them together, you get 100. Yeah. P equals 2 works.
So there might be like more than one A for P.
So this is, I think there should not be ever more than one a if it works.
There's only one.
So if it works, there's only one, because like if you increase a by 1, right?
Then that goes too much.
It either goes too much or it doesn't. You know, like the thing increases as a increases, right? So if it's too high and you decrease it, right? It'll just keep going down until it goes past. Once it hits it, you know, if it goes up or down, it'll increase it, so no, it won't be equal. You know what I'm talking about?
Yeah, kind of.
Yeah. So basically, like, if an a works, then there can only be one that works.
If you increase the A, then like the last part definitely increases,
Yes.
and the other parts might increase, so it
Yeah.
can't be the same. And if you decrease the same thing, the other stuff might not decrease, but the last one definitely decreases.
Because it's
Or the previous terms definitely don't increase.
Yeah, they definitely don't. Yeah, if you increase a, they definitely don't decrease.
Yeah.
And if you decrease a, they definitely don't increase.
And since definitely like always increases or decreases with A, then,
Yeah, I guess that was. And we try p equals 3. You get, so you I mean, you basically need to find, like, I guess it's sort of like 100 equals like a on 3 plus 2a on 3 plus a. So you're kind of looking for like p equals 50 or something. Well, a equals 50, right? Yeah, so can you basically tell me, one of you two tell me if P equals 3 works or not by the end?
I think it works.
P equals 3, what would A be?
50.
A is 50. So if A is 50, right? And this is A over 50 over 3 for plus 100 over 3 for plus 50, right? Plus 150 over 3, yeah? So this is like 16 something, isn't it? So it becomes 16.
Oh, I can never.
And this is 33 something, so it becomes 33.
Or just think
And then it is.
So this is 99, right?
51 is too much because it increases first. So
Oh, I can. It's I think 50 by 3 is like 17.
Yeah, and then 51 is too much because you make it
51.
51 and then this will go up by 1, right?
Yeah.
And so.
No, not 101.
It's 100.
So this will plus 1 and this will plus 1, yeah?
But it's 102.
Oh, sorry, yeah, 102. So they're all plus 1.
Yeah.
Okay, my bad. And so P equals 3 doesn't work, yeah?
Yeah.
So P equals 2 works, and P equals 3 doesn't work. P equals 2, P is not 3, yeah? And then we also notice that there's only one A, yeah? At most one A. That's good. So that actually gives you a really good way to try out the cases, right? So every case, every one A, basically.
P equals 4.
Right.
I think.
P4 is not a prime, but yeah.
4 is not one yet.
But I think this question we can try to generalize for non-primes too. So it's like if n was 4, so n was 4, n equals 4 works.
4 because yeah.
Why does that work? What's A?
Oh, no.
It's actually 67.
Well, yeah, it's
What A if n equals 4?
40. Because you get 10.
14.
14.
40. Okay. Well, yeah. We know this it's not prime, but let's have a look at it anyway. So that gives you 10, right? Plus.
Because then 40 over 4 is like 10. And you get 10 plus
Yeah.
20 plus 30.
So 40 over 4 is 10. So then it's 10 plus 20 plus 30 plus 40. And that's 100. Yeah. Can you tell me if 5 works? P equals 5.
I think if A is 50,
It does work. A is 50
I think it's 34.
for this one.
Yeah.
So P equals 5.
it's 10 plus 20 plus
50 on 5.
20.
Oh, I see. So hold on. So this is 10 plus 20 plus 30. No, it's got an extra 50 here.
Oh,
Oh, yeah.
So that means A is less than 50, yeah?
yeah, because they should be like a third of 100.
A third of 100.
Because you get A over 5 plus 2 plus 3 plus 4.
Yeah, so like A equals 33, for example. So you have like 33 on 5 plus 2 times 33 on 66 on 5 plus 99 on 5 plus 33 at the end plus 120, 132 on 5. Yeah. So this is 7. No, this is, sorry, that's a 3. It's 6 plus 13 plus 19 plus 26 plus 33 plus. So that's 19, 38, 71, 97, right? 97. So if it's too small, what happens if it's plus 1? Yeah, if you plus 1, then this will be plus 1. That won't go to the next. Well, times by 4, so it'll be plus. So that'll plus 1, right? This is plus times 3, so this is plus 1 as well, yeah? But this is plus 2, which is not plus anything, yeah?
That works.
So that works, yeah? So 34 gives you. So P equals 5 works. P equals 5 and A equals 34. Yeah? You notice anything?
2 and 5 divided 100.
Yes. 2 and 5 divided by 100. That's true. 3 does not. You also notice the A's are getting, so I'm just kind of telling you what I noticed at this point. So the A's are also getting smaller. Yeah. Yeah, like if A's are getting smaller, they can't go smaller forever, right? So actually, can you see that A can't even, so A obviously can't be negative, right? Or 0. A can also not be 1, right? Yes? Because all these would then just be 0, 0, 0, 1, right?
Yeah.
So A has to be like 2. So imagine if P was like infinite, right? It's really big, yeah? I mean, what would happen? So like, there'd be sort of,
Okay. If P is like greater than 200, I think, yeah.
Yeah, we don't have to refine it just yet, but like if it's really big, right? I mean,
So
you're going to get a ton of terms at the end that's going to be like 0.999, you know what I mean? Because P minus 1 on P is going to be like really close to 1, right? So it's like 0.999, 0.99. So even if you have A equals 2, right? you're gonna have like hundreds of terms that are more than one, right?
Yeah.
Does that make sense? So P can't be that big, right? Because A equals 2 is the smallest you can use. Yeah? So yeah, and then Haibing knows that means P has to be basically less than 200. And that's a huge thing, isn't it? Because now you have a case bash at most on your hands. Yeah. So suppose P is greater than or equal to 200, right? Yeah. Then all the terms that are like, and then A equals 2 is the minimum possible value, right? Then, when it gets past halfway, it'll be like 100 over 200 times 2, right? 101 over 200 times 2, 102 over 200. You know what I'm talking about? And so on, right? And all of these are bigger than half, so you'll always get 1 from the 2, and you get like 100 times, yeah? So that'll already give you 100, but then you're plussing 2. So how many hundreds are you getting? So then basically you're getting all the numbers from 100 all the way to 200, right?
Yep.
Which, how many numbers are there? There's 101 numbers, right?
Yep.
So
101 numbers in the last one is 2.
yeah, so there's 200 numbers from 1 to that, and there's 99 numbers up to 99. So it's 200 minus 99, right? So there's 101 numbers which are all more than 1, yeah? So it's more than 100.
Yep.
So that's like that's optimism, in a nutshell. Because before it's like, and if you do research, this is like basically solving it, because research doesn't have this 4-hour time limit, so if you can bound P, so P now has to be less than 200, right?
Yeah.
If P is 197, I'm pretty sure.
Oh, did you try that before? Or
No,
just
I just read it now.
Oh, it does work, I think. So what's the biggest prime less than 200? 199.
Yeah.
So is it obvious 199 is prime?
Yeah, calculate.
Yeah. So basically, how do you check if 199 is prime? Do you know?
Square root.
Yeah. So we don't have to check past like 14, right?
Yeah.
So we just have to check
The hard ones.
13, 11, 7, 5, and 3. Yeah. So obviously 7. So obviously 5, 3 don't work.
Yeah.
7 is 7.
Try it,
Oh wait, is it 7? No, that's 59. Yeah.
Yeah.
The mod 7, that's 59. Just not divisible by 7.
Also
13. So that's 69. And 69 is
It's 65.
So what else?
huh?
It doesn't work.
So mod 13 use. What are you talking about?
Like just
There's a rule for 30.
Oh, we don't even need the rules once we got modular arithmetic anyway. Yeah. Well, yeah, 13 minus 130 minus 13 minus 30. Okay, so it's not divisible by 13, yeah?
Yeah.
So it's prime. Does it work?
So if you have to use like 2.
So let's say A equals 2, yeah? Then, so what is it? So it's going to be
From 100 to
so
199.
from 1 on 199 all the way up to, what's half of this? 99, right? So that's not getting us halfway.
Yep.
Yeah? And then the ones from 100 to 199, they're the ones that get past halfway, right? So let's say 198, and then there's a separate plus 199, yeah?
Yep.
And so these all contribute 1 each, yeah? So each contribute 1, and how many are there? So there's 198 minus 99. So 99, yeah? Plus
2.
9.
Oh, 2.
2, yeah. Why didn't you correct me here? Okay. So that's 101, right? That's too big.
Wait. Why is it?
Huh? Oh, because this is A. Yeah.
Oh.
Maybe 2.
P cancels. Yeah.
2.
So when you leave the mistakes on the board, what happens? Are we? Yeah.
Yeah.
We're good. Okay. Yeah. Just let us know if it's all good. So.
What is it from 100 to 108? You get 1. And 200.
So from here you get 0, right? Because it's less than half. And the ones that are more than half, you get 1.
Oh, you multiply it.
Yeah. So all the A's are 2. Yeah. So this will be 101. It's too big, right? So if you lower A by 1, or A can't be 1. We said that, right? So we're already done. It can't be 999. Yeah. Are we in agreement?
Yeah.
Not 199. So and then what's the next biggest prime?
1.
197.
So obviously not 3, 5, 7, 11, and 13. Yeah. Does it work? That's the question. Yes. Oh yeah, I guess that counts because you did it just then too. So 197 works?
Yeah.
For A equals 2. Yeah. So what do we have? So 1 all the way up to 98 doesn't do anything, yeah? But then 99 on 197 starts doing stuff. All the way up to 196 out of 187. Yeah?
Mhm.
And there's 98 of these, yeah?
Yeah.
And then plus 2 from the A. That makes sense? So each of these give you 1. These all give you zeros. 98 of them plus 2 is 100. So that's interesting because we kind of said P is less than 200, but you can't say like it's always less than 100 because it's not, right? Yeah. So
Wait, so is that P dividing?
huh?
Like it says something about P dividing.
P divided. Yeah. So this one no longer divides 100. Yeah. Yeah. But it still remains to be a square plus 1.
Oh.
Huh?
Oh.
Oh, I didn't know. I didn't know. I didn't do anything with that though.
Okay.
But I'm just saying.
Yeah. But next group.
Power of 2 plus 1. No, 14. Sorry. Okay. Let's just get
Next
excited.
group plus 1 is it?
Yeah.
So
None of the other ones are. Yeah, 37.
Yeah. The 37 didn't work, I think. I don't know if it works. And then A plus 2. Yeah. Yeah. Alright, let's keep going. Yeah, I guess the depending on you can choose your own destiny now. Trying 37 was something I thought was interesting to do, but I can tell you what happened. I didn't actually go through with it, but I was about to. And then I said, hey, you guys could do it too. Alright, well, shall we do 37? We mentioned it, yeah? Okay. But let's see, A doesn't have to be 2 or anything. Oh, okay. I remember why I didn't actually try at this stage because I didn't have an idea where A had to be. But later on I knew it had to be like 5 or something for this. Wait, what would A have to be for 37 to work? 5 or 6? Or we can Let's try a equals 5. Yeah. So 5 on 37. Is this?
Mm.
Yeah.
So it's like 35 and doesn't do anything.
Oh yeah. Not enough space. So. Oh yeah. Okay. Well, I guess I was going by fifths then. Yeah.
Yeah.
So if you go from 1 all the way up to what's the fifth of 37, like 7, right? 7. So 37 is 7 and 2/5. Yeah. So all the way up to 7, it's going to be less than a fifth, right? So that's going to give you 0. If you go from 8,
Yeah.
huh? You got 8. So if you double that, it's 14, right? You go up to 14, it's going to be less than 2/5.
Yeah.
So there's going to give you 1, and then 15. That's when it goes to 2/5.
Mhm.
But 22 is still less than 3/5.
22, yep.
So it goes to 22. That'll give you 2.
Yep.
And 23 goes over all the way up to 28, 29. 29 gives you 3, right?
Mhm.
And then 30 to 36 gives you 4, and then plus 5, yeah?
Yeah.
So that's 7. There's 8. 8 numbers here.
Yep. And there's 7 of those.
Yep. And then there's 7, yeah?
So that's like. 77.
77.
Yeah.
What a bad choice of it. Really? 77?
Wait, is it,
7 plus 6.
8, 56.
77.
that was sad.
77. Okay, so this is 77. Let's
77.
increase A by
2 or 3.
2 or 3.
I mean, if you increase by 5, it makes it easier. But it's not going to be wrong. So.
Do you want A equals 7?
8.
8.
Why
Oh,
not 8?
jeez.
8's not that bad.
8.
No, good.
Okay. Yeah. 6 goes over. No? I feel like 6 would go over, wouldn't it?
6 would I don't know if there's enough time for it to description of up to 6.
Oh, we're going to split the work.
Are you doing 7 or 8?
1 to 7.
I'll do 8 then, I suppose.
Alright, and I'll just
What is
ponder life.
8 over.
8 over. It's way over, right?
Yeah.
Yeah.
Let's see if I can do 6 before they're done.
I'll do 6 as well then.
Yeah, I guess that was too long. I might not be able to. And then we'll start.
There's no happiness.
Equals 6. So A is not equal to 5. A equals 6, for example. 1, 2. This is 6. So this is 6 and a 6. Oh, it's like the only time I've used mixed numerals in maths in my life. Except when I had to like teach it or something.
I'm pretty sure that's one. But I'm probably going to say check.
It's like mixed numerals is just like you don't write the plus sign.
Yeah.
But like you want to not confuse everyone at the same time.
So easy and proper.
So you say it with a plus by using the
Yeah,
word
I got
and.
95, but I went.
Okay, so 7 all the way up to 12.
Oh, this is so long.
13, all the way up to 18, 13, right, 24, 25, 26, 31, 36, 36, and then plus 6, yeah? So that's 0, 1, 2, 3, 4, 5.
I should say 30.
Huh?
I should say 30.
25 to 30. No, I'm not. So 24 and 4/6, right? That's 4.
Oh, yeah, they're the same.
No, this is way over. This is way over. 7 is way over.
Yeah, so 6 should give you 6.
Gives you 94. Or 90.
I think these are all times 6, right?
Okay, so it's
So
all
it's just 3, 6, 10. So it's 15 times 6 is 90. 96.
37.
37 is annoying number.
Huh?
96.
Oh, then
Yeah.
37 is work. 37.
Oh, so A equals 7 is way over, right?
Yeah, it's like 150.
It just sounds funny. Anytime it's like extreme, it sounds funny. Okay, so 37 doesn't work. Yeah.
Oh,
Okay. Yeah, I guess this came a little bit out of order because at some point I was thinking, because you know how like once we said it had to be when it was above 200, right? A had to be 2, right? Well then what like you know, for which numbers would like how would A equals 2 work, right? Like A equals 2 is very predictable. You need, for example, if P is less than 197 and bigger than 100, right? And A was equal to 2,
is
right?
there like an algebraic method to do this? Does it have to guess a check?
Well, I guess the thing is you're never guaranteed to find the method in the time, you know. But like the point is you're reassured that you'll actually get the answer at least because you know there's only so many you can check.
Yeah.
But yeah, like I'm like maybe there is, you know.
Is there like stuff possible? Because it seems weird.
Yeah. So can you see that if it's between, so P can't be bigger than 100. So if it's between, so let's say P is bigger than 100, right?
Yeah.
And A equals 2, right?
Yeah.
And it's less than, say, like 197. Right? then the sum is going to be sort of somewhere between 50 something, right? And to like, you know, something less than 100, right? Well, P is 196, maybe, but it has to be like, you know, odd enough. So the next one down is like 193. So it's going to be like less than 100, yeah? So A equals 2 is not going to work, yeah? And if it's like this, right, then A equals 4 is not going to work either, yeah? Is that obvious? Because A equals 4 will more than double whatever A equals 2 is. Yeah? So A can't be 2, A can't be 4. Wait, is that what I actually did? So it has to be either, it has to be 3, right? A has to be 3.
That's 3. If you just test it with like 100, I'm pretty sure they do.
Yeah. So if you have A equals 3,
Test it with something simple.
so anything worth like a third of it. Yeah, if it's bigger than 100, a third of it will be like, let's try it 100, yeah? A equals 3. So 1. What are you saying? Oh, is that what you're saying? Okay. We're saying P equals 100 then? Okay.
Wait, what are we saying?
So like, let's say P is bigger than 100, yeah? Yeah? Then 1 to 33. Be 0. There'll be like at least 33 numbers that'll give you 1 and another 33 numbers that'll give you 2, right? Plus a 3. So it'll be bigger than 100. Yeah?
Yeah.
Yeah. So like to summarize what we have, yeah? So we know like, so from like 100 to 200, there's like 197, yeah? And that's what like A equals 2. There's nothing here, yeah? Up to here, I guess we know that 2 works, right? 37 doesn't work. 3 doesn't work, right? 5 works. Was it 7? Well,
7 doesn't work.
doesn't work.
We don't know the
And then
answer.
so 11, 13, 17. Actually, I did check 19 already. 7, 13, 19, 17. What is it? 23? 29, 31, 37, 41, 43, 47. Let me say something here. $53. No, 59. No, yeah. I think you might be able to eliminate. See, because what was it? A equals 3. Sorry, what was it? A equals 6. What was too small? For 37, right? That
6.
yeah.
Doesn't 6 was what? So every A from 37 downwards is like less than 6.
Hmm. Maybe 3.
Yeah.
87. No.
It's 3.
89.
Yeah.
91. 97. And that's it. Yeah, that's it, right?
Uh-huh.
So somewhere A had to be because right here. Oh yeah, there was one more thing I was writing before. It was like, obviously, if you didn't have the floors, right, you'd get like 100 P equals, A out of P plus 1 times P over 2. Yeah? And so the P's cancel, and it's 200 equals A times P plus 1. So the A that you get here will always be smaller than what it should be, right? So for example, if P is P is 40, right? 41, then A has to be like around 5. Yeah. So we know that like yeah. So the A's are decreasing, right?
Yeah.
So if the last one was 10 and this has to be greater than 5, then it can only be 6, 7, 8, or 9. Maybe more extreme. Maybe more extreme an example if P was 70.
Pretty sure I tried 3 and 4 for like, so if you try 97 for 4 for 3, I mean,
Mm-hmm.
you end up with like, it's like slightly off, so it can't be. So 4 probably won't work. But so 3 probably won't work because if you try with 97, it's slightly off.
So you're saying A equals 3 doesn't work for anything?
I think so. And I tried 53, like around there for A equals 4.
Mm-hmm.
And it's also very slightly off. It's like a 102
A equals 4, you said?
Yep.
For 97?
for 53.
53. Yeah. Yeah.
you guys want juice?
And some water?
Yeah.
Just some water. Oh, the AI movement. Did you show us one that you sold? 2012. Where's the book? Oh, you want one of these? Huh? No, I did it. You know what that is? I'll try it. It's kind of unique, so it's just that thing. Got another one. Pretty small. One time we did 4 points. No, you can also just give me one. So 2012. If I told you it's made from fruit, it would make it better. That does not change it. Oh, the triangle number. Triangular number is the sum of both ends. The Tn is the sum of both ends triangular. Derive a formula for Tn, cancel our line, prove that. Is this the one you did or? This one is one with 9 and 10 have the 1 to 8. Five contains a certain number of 5, 10, 20 cents, 50 cents, one lower point, more than one denomination. For example, if the bag of pop if it contains 9 5-cent coins and 1 20-cent coin, then it contains exactly 10 coins and 2 cents. Notice in this example that if any single coin is removed from the bag, there's a denominator is like around 25. Notice in this example, if any single
It seems like
notice in this example that if Oh, maybe you can explain that question to us with the 5 problems each person two problems. It's like what do you see that table. So you're busy Wednesday or not Friday?
This Friday I'll be.
Oh, you're fine. Is it a time limit?
45 minutes. No, like their school, like we did it. Their school that like around 30 minutes, and then like 1 hour, like somehow I was playing my run out of time, and then like but then like normally we go play with it, and this time they come to our school, so we were running out of time.
Is it 3 or 4 people? You,
4 people.
you, Eva.
And 2 other people from our grade. There was one year 9 guy, but like he's worse than our other players. We have 2 reserves. And I have English homework, I think. What is it? I don't remember.
Okay, so when's chess? It's like 5 o'clock.
Like starts like 3:30.
Oh, when does it finish?
When we finish play, so it's probably around.
2 hours max, right?
Yeah.
Oh yeah, my mom wants to know when the lessons are on. Like,
Oh yeah, so you could probably come on Wednesday or Friday, but you could come later on Friday.
Come later on Friday, maybe.
Yeah,
If I'm bothered to use my brain after chess.
yeah. But yeah, I think Wednesday or Friday I'll
could
leave for
even
maths.
So it's on every Sunday.
And those games are going to be. They're all 700.
Because he can't come Sundays, so
No, I can come sometimes. I just
not every Sunday. Yeah.
I can come every Sunday. It's just
Weekends.
Useful.
yeah.
Yeah.
For like
Crowd
crowd
for nothing.
Yeah, so we have it every Mondays. Every Monday.
One day you don't
But
know anything.
since the senior contest is on, I think I'll leave my time open for Wednesdays and Fridays as well. Yeah.
I'm free Wednesdays because I finish school early.
Yeah.
Yeah.
Oh, you're free
that's
Wednesdays
cool.
too.
Yeah.
Maybe you want to come on Wednesday as well. So the test is on the Tuesday of next week, right? It's the 20th.
20th is Tuesday, is it?
What day is it today?
It's
Today's the 12th, right? So tomorrow's Tuesday the 13th.
Okay.
So it's Tuesday the 20th, yeah? Didn't you read the schedule I gave you on the back?
That was a sketch. That was the schedule on that. Okay.
Yeah. Yeah, we'll sort it out. I have to quit Scouts. Do you want to explain 9? Or do you want to explain what was the one you did? Was it 3 or something?
3.
Or you could just like lead us through the problem. What is the problem? Oh yeah, so you have like a maths exam with 5 problems, yeah?
It's like this one.
And each student they get two or more correct.
But not all 5.
Like they get more than 2 but less than 5 correct. Yeah. And that's terrible. Sorry. And for each pair of problems, like questions 1 and 2 or something of problems, exactly 2 students got them both correct. I didn't quite understand what the pigeonhole principle was used on.
Oh.
What the pigeons were.
It's for each one.
And what's the minimum number of students?
Oh, that's the actual question, yes. The question is, what's the minimum number of students you could have that satisfy these conditions?
So exactly 2 students got like every pair correct. Yeah.
No, for every pair, exactly 2 students got yeah.
So every 2.
So like say
Got both correct.
Questions A and B, then two students got both A and B.
Yeah.
So exactly 2 students got A and B. And like A and C, 2 students got A and C.
Oh.
Yeah.
So,
But like there could still be like another student that got one of them but not both of them.
Oh, but they have to be 2. So, yeah.
Like
But
it's just, there's exactly 2 that got them both right, but there could be any number that got
because
1 or
right, yeah.
0 right, or whatever that means. But maybe they they might not be in the end.
wait, for every pair, like, does it have to be consecutive or can it be 1 and 3?
Oh yeah, it's not consecutive. So any it could be like 1 and 3, or 2 and 5. Yeah, so I guess it's a 1 student, 1 work, right? 1.
It has to be 2
You
different
need at least
students.
2 yeah.
Huh? Yeah, like if 1 student gets A, B,
You need no one to get A, B.
or C, or D, right? Like they say they get 4 correct even. The point is there's at least 1 that they can't get correct.
Yeah.
And so that anything that pairs with that will create a problem, right? So it can't be 1 student, you know? And see, I think that's a better way of saying. The thing with 1 student is it's kind of obvious, right? But I think there's still a better way to say certain obvious things.
Yeah.
You know what I mean? It's like 1 student. It's better than just saying it's obvious. You can say, well, there's at least 1 question they didn't get correct, right?
Yeah.
And so any pair with that 1 question will
Okay,
will lack 2 students that got them both correct. Yeah, so maybe that argument works for 2 students as well, right? So say they're missing. So this one is just not D, right? This one's not E, yeah? Then DE has not 2 students, yeah? Or if they're both D, then D anything will not have 2 students, you know? So students, so that's truth. If this works all the way to 5, then it means you could have written it more explicitly. But it's slowing down. but it's like not A. This is like not B. This is like not C.
And yeah, after this point, then now if you write them out, you'll realize that there are two like questions they all got. So that's why I meant by repeating home, but I'm not sure explain it yet.
Is it 2 students?
2 students.
Yeah.
Oh, we say it can't be 2 because if it's 2, right, that person must have got A wrong, right?
Yeah.
And B must have got 2 must have got B wrong, say, yeah.
Oh, why can't 2 get 5 wrong?
5 wrong.
Yeah, so
Oh, they have to get at least.
I
2
mean number 5 wrong.
Oh yeah. So they get E wrong, right?
Yeah.
But then AE is a pair that doesn't have 2 students.
Oh yeah.
Yeah. Okay. So 3 students. So they're like not A, not B, not C. Yeah. Then BC must be a pair.
DE must be there's 3D. DE
Huh?
must be a pair in all 3 of them.
Oh, I'm not saying that they all got everything else.
Oh, okay.
I'm just saying they have to have missed one of them. So let's say like AB, right? That pair for that not to have been 1, right? Then 2, 3 must have got A and B, yeah. Yeah. For BC, yeah. Sorry, this is bad. I should write it better. Okay. So that's at 1. So 2, 3. These are the students, right? So this is what they got, and this is what they didn't get. Okay.
Yeah.
Right. So say they didn't get some different stuff. Yeah. Then compare AB.
Must be
They if neither 1 or 2
can get AB.
got them, oh, that's already a problem.
Yeah. So it has to be more than. So you have another D. So you need at least 4 students for this case, type of thing.
Hold on. So A and B needs 2 students to have gotten them both right, yeah?
Yep.
And it can't be these 2 students.
Yeah, so it has to be 3 and 4.
Yeah. Okay, so that's if they're different, okay? What if they're all the same? If they all didn't get C, then C must pair with something that none of them got, yeah? Okay, so that means it can't be 3 students, yeah? And 4. Yeah, so they can't all be the same because then that's the same argument, right? So there has to be something different. Look at the lowercase. This is what you like to do. Sorry. Is that called trolling?
Yeah.
I don't know. Like, before we just did them without knowing what they were called, and now we have names for them all. Okay, so then these must have gotten A and B, right?
Yeah.
Is it 5?
Oh, jumping ahead. Is 4 obviously wrong?
I'm not sure. No,
Because if 4 works, then 5 automatically. But if 5 works, ooh, contentious. Hold on. So
I refuse to believe 5 works.
Yeah, I'm pretty sure that's
But then if everyone got 1 more, they got different.
Exactly 2. So if 3 people got like
Ouch. Okay, never mind.
okay, so CD.
Yeah. And then you need the you need D and B somehow.
E and F or D and B. Oh yeah, I need to pair them up differently too. Yeah.
Yeah.
So that means they have the B.
Yeah. So that one needs a B and the other one needs a D. No, not that one. That one needs a D.
Oh,
So number 3 has a D.
D. Yeah. Oh, so that is we can 6 pairs. Yeah.
yeah, the 6.
6 pairs. So we got to pair them up like that, and then we just did that, right? We can also pair A and C then.
Yeah.
So that means A and C must have been gotten by these other guys. So this is A, this is C, yeah?
Yep.
Are they the only other pairs?
And then you have E.
Oh, what happened to E? So did they all get E?
If they all got E, then you have too many. You have too many A's. Or
What?
yes, because you need exactly 2.
Oh,
Wait, so doesn't?
oh, they can't all get E.
Yep.
So only, how many of them can get E? Two of the 3 can get E.
Yep.
So the other one who doesn't have E,
Gets no. Yeah, the other 2 don't have E, and that is very good.
let's give these 2 E's.
Yeah.
And this person doesn't get an E.
And the person doesn't get E either.
Huh?
The top person getting E. The top person can't wait.
You need a C.
Yeah.
The top person can't get an E either.
Yeah.
D,
You need a C.
So now you need another C.
that's bad.
Yeah, because you need a C and you need like a P.
Oh, so you can't get a C.
But you can't have a C and a B together because then you need B C.
So you can't.
You can't have 5 people.
So they say 4 people can't one,
No.
Yeah.
and that's 4.
Oh, boy.
I think the fact that there's you need exactly 20 pairs.
Yeah. So what does that mean? 20 pairs.
And so the way I wrote it was if you have a student that has 4 problems,
Yeah.
then that would
So
only have 6 pairs.
Yeah.
Yep.
Oh, I know to find 20 per since 4 is the maximum, just do 20 divided by 4.
Well, but for solving 4 problems makes you 6 pairs.
Yeah.
Yeah.
So 4 choose 2 is 6.
Yeah, and then
Oh, yeah.
so you want to maximize the amount of 4 you have for how many times you did 4 problems, and then so if you try that, you realize that if you have 3 students who did 4 problems,
Mm-hmm.
then they did together they did 12 problems,
Mm-hmm.
and since there's only 5 problems altogether, so that means at least at least 2 problems got repeated 3 times. Got written in all 3. Got solved in all 3.
Hold on. You said it again. So they did 12 problems.
There are 12 problems.
Yeah.
So there's a pigeons.
Okay, there's 12 problems as pigeons.
Yeah, and there's 5 holes.
There's
5 holes.
5
So there's one there's one problem has got
Tree.
so one problem got 3 students solved it, yeah?
Yep.
Okay.
And each one has a maximum of 3 pigeons in each, because you can't have 3 students solve 4 of the same problems. Can I just try to write it? It's probably easier to just write it out. So first student solves A, B, C, D. Second person solves A, B, C, E. And then next person solves A, B, D, E. Then we can see that it's A. So all the A's have been solved, and all the D's have been solved.
Mm-hmm.
So that means the AD pair is solved 3 times.
Oh.
And since because no matter how you do it, you always get 3 of them that have been solved. 2 of them that have
Oh,
been
so
solved
he was
3
saying
times.
if there's more than 3 people solving 4 problems, right? Then there's going to be 3 problems that have been. There's going to be 2 problems that's going to be solved by all 3 of them. Is that what you're saying?
Yep. So then if there's 2 problems that are solved by all 3 of them, that's wrong. Then that can't be true, because exactly 2 students got every single pair.
So
that means there's a maximum of 2 students to solve for.
Yeah. So what are the pigeons and what are the holes? Or does it not maybe not matter then?
It doesn't matter anymore after you get this, but like the pigeons were the questions,
Okay.
and the pigeonholes were the pigeons were the solved questions, and the pigeonholes were the questions.
So if you solve 4 problems.
So basically, 2 of them had to be solved at least 3 times. 2 of them had to be solved 3 times between the 3 students.
Hmm.
So then after that, you know that 2 students solved 4.
Yeah, I guess another way of saying it is kind of like what we were saying before, right? Like if you don't want A to be solved 3 times, one of them has to be missing A, right?
Yeah.
That can only be missing that A. That's fixed. And if you don't want to be true for B, then the other one must be missing B. If you don't want to be true for C, then that one's C.
Yeah,
but then it has to be
D
true
and
for D and E. Yeah.
So you have 2 students to solve 4, and in 4 there's 6 different things.
Mhm.
Yep, and then so that's 2 times 6, which is 12 pairs. So so if you solve 3 problems, that's 3 pairs, and 2 problems is 1 pair. So now you have 12 pairs, and you want to make it minimize the amount of students with either using 3 pairs or with 3 pairs or 1 pair. So then obviously you just have 2 of these and 2 students to solve these
To get 20.
to get 20.
Um,
And now we know that 6 is the minimum. So once we show 6 is possible, then we know 6.
yeah. So I like that 6 was possible because that was very explicit.
Yeah.
20. So what exactly is the claim about 20? So there's 10 pairs of problems because there's 5 choose 2, right?
Yeah. And then each one is solved twice. So there's 20 pairs of problems that have to be solved.
So the pairs are solved twice.
Yeah, each pair is solved twice.
Yeah, okay.
So and each all the pairs of the problems that students solve have to add up to that many pairs.
Mm-hmm. Yeah. And so why does so I can see why that's at most 2, right?
Yeah.
Most 2, right?
That's a must do, yeah.
Um,
If you use more than 2 of these, you'll get over 20.
if you use more than 2 of these, you'll get over 20 straight away.
Yep.
Because that's 9,
Yeah.
right? But why couldn't you use less?
Oh.
So is it because they won't ever add up to 20? Is that what you're saying?
Oh no! If you use less of
use
these,
the
then
least
you're trying to use the minimum amount of students, right? So you want to maximize the large numbers.
Oh, okay. Yeah. So you won't even be able to get to 20 then if you use less. Basically.
Yeah. If you use less, then you go 1, and then you go. Oh yeah. If you use
So what
1,
you're
you
saying?
need 4 of these, and you need 2 of these. So one of 6, and then so you need 14 out of these 2.
Is that impossible?
Well, 4 of these and 2 of these, but that's already 7. So that's not good.
7.
Because 4 of these plus 2 of these plus 1 of these is 7,
Yeah.
and you've already been able to make 6.
I'm sorry. I'm not really following.
Okay, so you have 1 student who solved 4 problems, then
Yeah.
that's 6 pairs,
Mm-hmm.
and then to make 14, you need 14 out of these 2.
Yeah. So you have
You need to maximize this then, because otherwise it's too small.
okay.
So if you maximize this out of 14, you can put 4 of these 3 people who solve 3 problems,
And then one of those.
and 2 of those.
Oh, okay. Yeah.
Yep, but that's 1, and then there's 4, and there's 2, so that's up to 7.
Oh, there's more people. Is that what
Yeah,
you're
there's
saying?
more people.
Okay.
So then, yeah. So basically, after you do this, you just show that it's possible to get 6 and do it with 6 people.
Yeah. So basically the only way you can add it up to 20
The smallest way is with 6 people.
is 6. Okay. I think that could be explained more explicitly or shorter or something. I don't know. Like it just feels the argument feels harder. Sounds harder than it is.
Oh, yeah.
Yeah, I guess the 20 student pair thing was a bit confusing too. It's exactly what that was.
Oh,
It's like a pair. Yeah, 'cause I guess we only cared about students that solved a whole pair of problems.
yeah.
And you needed at least one of those students for every. You needed 20 of those kinds.
Yeah.
Why is it 20?
Oh, because there's 5 problems, right?
Yeah.
So there's 10 pairs problems. So then each one solved twice.
Ah.
Yep.
Oh yeah, did you want to write up the combination that you had
Oh, I think yeah.
for 6? Yeah.
Wait, what question is this?
This was
Question of 3. Oh,
was
some other things. Right?
this one.
Question.
I guess we kind of just showed you just then.
Oh, okay.
Yeah.
What are the first 2 problems of that?
What's the AMOC?
It's like, I guess it's what people have to do once they get, like, I guess once they did well once in the AIMO, and they no longer are fast enough to do the AIMO.
Yeah.
They have to do this now.
Yeah.
It's just like, I guess this is just like, I mean, out of all the ways to get to the selection school.
Yeah.
there's
This is okay. This is like
was
this is basically like the the exam to get into team selection,
oh okay.
and the people who get into team selection get like full marks for this, which is like
But like in year 10 or something.
well like yeah, like if you're in year 11, then like you probably have to get full marks to go to year 12. Because they don't allow that many year 12s.
Yeah.
So
So like 3 people or 4 people get full marks.
I don't know how many.
Well, for the 2014 it was like 3.
Oh, okay, yeah. Like how many people got closer?
Maybe, oh yeah, I can check actually. I can check it. So for that exam, had like, see the ADDIE ones. It had the ADDIE ones. That was question 1.
Oh.
It has that one we just did question 3, and it had that one we did as 5. And so if you want to see the stats for that, it's sort of,
This is AIMO.
huh?
I thought this was AIMO.
Oh no, but we're doing this to help you with the proof part of AIMO, because these are all meant to be, well,
Yeah, they're all 7 marks, and it's not just answers.
yeah. Because that's probably the thing that's most unfamiliar to you. Let's see. This is
That's like a way of doing 6 students, such as possible.
yeah, so student 1 gets everything right except for the last question. Yeah. I tried to introduce capital letters so it wouldn't be a random notation, but it still appeared random.
But in like a test, is it sufficient just to write that?
Well, I mean, in like it's people are actually looking at it, so if they can understand it. No, it's like, so so if you just wrote this, right? What you would prove is that the minimum is 6 or less. Yeah. So then you'd probably get like this would give you probably like 5 points,
Oh,
4 points, because that's a huge deal,
Yeah.
right?
Yeah.
But then why can't it be 1? Why can't it be 2? Why can't it be 3? Right?
Oh.
And so that's the argument you'd have to give, or some other argument like that, or like how I was going like 1, 2, 3 didn't work explicitly. Like you have to say so why it doesn't work for 1, 2, 3, 4, 5.
Yeah.
You know, and then that would be it. Yeah. So he's doing this test next Tuesday. So that's why we got like a lot of these things because it's interesting to us, and it also happens to be the same kind of stuff as the like a bit harder than AIMO, but you can still do it, right?
This one's easier than AMO. I like a lot. I think AMO is harder than this. Which is sort of weird because AMO is the one they used to determine if you're going there in the first place. But then they use this to determine if you're going to go to trial, so for team selection.
Let me have a look at the stats.
I'm like still scared. I just got lucky on the AMO this year, and that was easier than usual.
So senior contest statistics, page 80.
Page 80. I just saw people from my school. That's the school of excellence.
All right, so the questions that we just did, right?
Yeah.
So question 1 was the ADDIE question, yeah?
How many students did it?
There was basically like 80 people.
88, 90 people, yeah.
90
like
people.
80 people, yeah. 88 people.
77 got 6 or 7. And
I got question 4, so like, it's probably pretty.
so question 3 was the one with that one just did the exams, yeah. That one was question 3, and there were 25 people that got 0.
And 20. Oh, it's like 25 people.
And then 25 people got 7 out of 7. And then like scattered between like 5 people got 1, 11 people got 2, 2 people got 3.
Like so many people got 6 years.
Yeah.
Like the ADDIE problem. No, I think a lot of people got 6 on.
Yeah, maybe they didn't say the converse.
Oh yeah. That's the people who won.
Does it tell you? Yeah. So what was the cutoffs? If you got
Yeah. So there's that.
So 3 people got perfect scores.
Yeah. Oh yes. Okay.
They're all in year 11. Yeah.
Wait. He's a like lecturer there.
Who?
Zhongmin is his called Johnny, but yeah, he's a lecturer there, and Matthew Chia went IMO in that year. Matthew Chia went IMO sometimes.
Anyway, so this is like
So
the high distinction. I mean, there's only like
and when minus was like it might be in there.
Yeah.
Oh yeah. Like a lot of people from Scotch College seem to come.
Yeah. So in that year, if you got 3 questions right, you'd just be off. You'd just miss out distinction. If you got 4 questions right, you would be at the top of distinction.
Yeah.
And if you got more than that, you get high distinction or prize.
Yeah.
Yeah.
4 questions correct.
Yeah. So for this test, you need 4 questions.
4 questions would be around.
So 4 questions, and you got nothing in all the other ones. If you got 4 full questions, 7 out of 7, and you got 0 in all the other 2, in the other one, you'd get distinction cut off, like high distinction cut off. You wouldn't get high distinction. If you got 1 more point in the 5th question, then you get a high distinction. If you get another three more points,
I think the last problem point just determined these guys.
yeah. If you got the last problem completely right, or you lost just 1 point, you'd get a prize. So if you only lost 1 point, you get a prize. 34 is a prize.
Linus was like year 8, no, year 9 then.
But only year 11's got prizes.
Oh yeah.
Oh, is it possible to get a prize in year 10?
Well, there's a guy who
It's
got-
possible, but
Yeah.
it's not often. I mean, there's one year 10 that got 29 out of 35.
Oh, so
And,
looking at,
and,
I don't know his
and
name.
there's no year 8s in here.
Don't know his name.
can year
Probably
8
not.
take the test?
I
Yeah.
think so.
Yeah. Oh, no, yeah. There's a guy in year. There's a guy who's in intermediate in year 8.
Yeah.
Year 6 is going to take the test. Yes.
Like 1. It was like
2.
Has
One
there
was
ever been
Russian,
a
so
year
like-
6 who got like prize?
maybe.
Yeah. The other guys. So that if you score. I think she's like she won an IMO like, and she's also a lecturer. Where's the guy called William? Matthew Chia. So the like 10-year-olds. That's the like guy's brother.
Oh, okay.
He won IMO like in year 12. So and his brother's 10 and he's in the thing. So
Yeah. Yeah. So basically, if you do well in AIMO, you don't get necessarily invited to the senior contest, but you get invited to like AMO.
the yeah,
And AMO like
gets you into
it gets you invited into lots of stuff.
Yeah.
Oh, so this is after the AM or before
This
the
is
AM?
The AMO is in February.
Oh.
AIMO is in September, and this is next week.
Oh,
Yeah. Yeah. So if you want to come back for Wednesday and Friday, we'll be doing more of this. When's your is it scouts or something?
cadets
Cadets.
on Wednesday.
When's that finish?
Oh, 9:30.
Oh.
what's good?
Oh,
Wait, doesn't yours work?
oh, yours mom's yeah.
Oh, it's
Let's go for it. Let's go.
oh
No.